Okay, let's continue the double integral. And we will continue the study along previous lecture for more general regions. That means type 1 region and type 2 region. So first, let's look at the following example. We want to evaluate the following integral, the double integral over the domain D, where instead of giving D explicitly, here we describe D in a geometrical way. So here D is the region bounded by the parabolas y equals 2x squared and y equals 1 plus x squared. Evaluate. Okay. I strongly suggest you first draw the picture for D. Otherwise, you may have a hard time figuring out the explicit formula for D. So this is x coordinates, this is y coordinate. And the first parabola, this one, has narrow mouth, so go like this, y equals 2x squared. And then this one, starting from 1, and because the coefficient before x squared is smaller, so you will have this. Okay, then the region D is given by this. Now we can figure out how to calculate it. So basically you have two methods. View D as type 1 or type 2. Here we will view it as type 1, but if you want to view it as a type 2 domain, then you need to do the following. You need to project down to the y-axis. Okay, and then just so what should you do? Actually, you should cut this into pieces. For each one, the y-coordinate is free and the x-coordinate is bounded by two functions of y. But you see from the picture, if you want to do this, then you need to calculate 3 domains independently. So the first one given by this, and then the second one probably given by this, and then the third one given by this. You need to calculate them separately. It's not that convenient. Here, therefore, we view D as type 1 domain. This is because if you project down your x is automatically free, and your y is bounded by two curves. First one is this, and second one is this. Okay, as you see, first one is this, second one is this. Okay, next you need to figure out explicit coordinates for point A and B. And we all know that those 2 points are determined by the intersection of the 2 curves. So next, we try to find out A and B by solving the following equation. So y equals 2x squared, y equals 1 plus x squared. And you substitute second one into the first one, you get 2x squared is 1 plus x squared, and then x is positive or negative 1. Therefore, A is negative 1, B is 1. Okay, then by the formula for the double integral over a type 1 domain, this integral can be written down as iterated integrals, an integrated integral as following. In the following, so first, your x is between negative 1 and 1, and then your y is between two functions of x. And notice that here the yellow one is above, is on the top. Okay, and the green one is on the bottom, so below. Therefore, here you should have 1 plus x squared, and here you have 2x squared. And then inside, just the function. Okay, next we compute it repeatedly. First, we do y integral of this guy. Then you have xy plus y squared evaluated at 1 plus x squared to x squared. Okay, then you have x times 1 plus x squared plus 1 plus x squared squared minus x times 2x squared minus 2x squared squared. Okay, next we simplify this by distribution law. X plus x cubed plus 1 plus 2x squared plus x to the fourth minus 2x cubed minus 4x to the fourth. And also you have dx. And here, then let's combine constant term. You have 1, so 1 here. And then for linear term, you have x. And then you have quadratic term, 2x squared. And then you have cubic terms here, so minus x cubed. And lastly, you have the the fourth term, you have minus 3x to the fourth dx. Okay, then you use power rule one by one. Here you have x squared over 2 plus 2x cubed over 3 minus x to the fourth over 4 minus 3x fifths over 5. Okay. And evaluate, and 1, negative 1. And then you have 1 plus 1 squared over 2 plus 2 times 1 cubed over 3 minus 1 to the fourth over 4 minus 3 times 1 to fifth over 5 minus negative 1 plus negative 1 squared over 2 plus 2 times negative 1 cubed over 3 minus negative 1 to the fourth over 4 minus 3 times negative 1 fifth over 5. And noted that all the monomials of even power are cancelled because your domain are symmetric with respect to the origin. And then for the order terms, actually you just double it. So you have 2 plus 2 times 2 over 3 and minus 2 times 3 over 5. Okay. And if you calculate, it will be 32 over 15. Okay, so this is this problem. So the key point is you need to view it as type 1 domain. Next, let's do a similar one, but this time we view it as a type 2 domain. So what is the double integral over xy over d? We'll evaluate. Where D is the region bounded by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Okay, so first, as the previous problem, we first draw a picture. And here, firstly, you have the line. So the y-intercept is negative 1, and then slope is 1. So you go like this. And then secondly, you have the parabola, but now the parabola, the mouth of parabola is towards positive x direction. The x-intercept is negative 3, if I should say. X-intercept y squared equals 2x plus 6 is 3. So this is because if you solve for x is minus 6 plus y squared over 2, or minus 3 plus 1/2 y squared. Okay. then you will have this type region. So the one, so this is your domain D. Okay, then you notice that if we view it as type 2 domain, it's easier. This is your A, this is your B. So your variable y will be a free variable between A and B, and then the corresponding x will between the yellow line and the blue curve. Okay, so next we will figure out A and B. So you set up the equation. Since the geometric meaning for A and B is that they are the y-coordinate for the intersection points. So the red line is -1 plus x, and the blue parabola is -3 plus 1/2 y squared. And then you solve it, you get -1 plus x is -3 plus 1/2 x squared, and then simplify it, you have 1/2 x squared minus x minus 2 is 0. Am I right? Oh, I made a mistake. So here you see the mistake. This is not y, so this should be x. So let's redo it. Y equals -1 plus x. X is -3 plus 1/2 y squared. Okay, then substitute 2 into 1. Then we have y is -1 minus 3 plus 1/2 y squared. You multiply both sides by 2. You have y squared minus 2y minus 8 equals 0. And then you have two solutions. One is 4, the other one is -2. Okay. Then here, B is 4, A is -2. So B is 4, A is -2. Therefore, we can represent our double integral as iterated integrals as following. xy dA equals y is from -2 to 4, and the x is between two so it's between two curves. So on the top you have red line is on the top, and then bottom you have blue one, blue curve is on the bottom. Okay, notice that here you should write down a function of y because you are integrating x. So you should have the formula, not this one. but x is y plus 1. Okay, so here this is y plus 1, and on the bottom you should have this, so negative 3 plus 1/2 y squared, and inside you have xy dx. Okay, then let's integrate it. So first you do x integral, you have this, and then you plug in 2 endpoints. Then outside you have one more y integral. And now let's simplify it. You have y plus 1 squared y minus 3 plus 1/2 y squared squared times y, and dy. Okay, then the most straightforward way to calculate it is you just use distribution law and expand everything, simplify it, and then finally use the power rule for monomials. Or you can use integral by parts or chain rule, some fancy technique to solve it. So here, I will just use the most stubborn way to do that. Let me expand this. Q plus 2y squared plus y minus, and here you have 1/4 y 2/5 plus 3y cubed minus 9y dy. And as before, now let's collect terms with the same order. So here you first have this, so minus 5ths, and then you have cubic term. So you have, and also this, so plus 4y cubed, and then you have quadratic term 2y squared, and then you have linear terms minus 8y. Okay, so that's it. And then you will have y to 6 over 6, 4y to the 4th over 4 plus 3y plus 2y cubed over 3 minus 8y squared over 2, and plug in 4, negative 2. Okay. Then you have a lot of calculation of the integers. I will omit them here. So the final answer is 36. Okay, so I would like to make a remark. So, as we said before, here we can divide D into small pieces such that each one is a type 1 domain. Therefore, you can use the type 1 domain technique to compute each of the small integrals and then sum them up. So for example, for the same region, you might cut in the following way. You cut like this, so this part is a type 1 domain. And also, let me use another. This part is another type 1 domain. So the total integral equals integral over green plus integral over yellow of the same function. I will not carry out the procedure here, but I should say this is also very important because in general you cannot expect a pure type 1 domain or pure type 2 domain. You might have a combination of them, and for example, you might have the polygons. For example, you might have this one, and then you cannot view them. So you cannot write down, view them as type 1, type 2. But after division, you can always get small pieces which are either type 1 or type 2. For example, in this one, you can do triangulation. And each of them, of course, is a type 1 or type 2. Or if you are not satisfied with each one, you can do further cutting. I will not do that here. Okay. So next, let's look at one more example. So far we only studied the double integral of some given function. Next, we want to connect this method to the computation of the volume of some solid. Later on, after next week, probably I think we will give another way to calculate the volume. But I think I should say they are equivalent, but this one is a little bit easier conceptually. So the problem is like following. So find the volume of the tetrahedron bounded by the planes x plus 2y plus z equals 2, x equals 2y, x equals 0, and z equals 0. Solution. So first, let's draw a picture. So here I would like to take the coordinate as follows: x, y, z. This still obeys the right-hand rule. I just rotate a little bit because the main part of the objects we are interested in is on this part. It's on this octant. Okay, next I would like to draw the line x equals 2y. X equals 2y, so go like this. Okay, so actually this is a plane, but when you restrict the plane to the xy plane, you have a line like this. And then next, I would like to draw the restriction of this on the xy plane. So you will have this. And then notice that this plane also has intersection z equals 2 with a z coordinate. Okay. So this is the blue plane corresponding to this. And then this will be the red one. And of course, this one, x equals 0, is the zy plane, yz plane. So on the back, and z equals 0 is xy plane on the bottom. So you can imagine the whole tetrahedron and the consideration is O, A, B, C. So the tetrahedron and the consideration is O, A, O, A, B, C. And then if we want to compute the volume, we can express the volume as the following integral. Equals volume of OABC equals the integral over triangle OAB, and then of the function height dA. Here you view, you project the tetrahedron down to OAB, and then you view this is just like a cylinder, but not exactly cylinder. And then first, let's figure out what is the height function. So first, the height function should be a function depending on x and y only. And here for each fixed point on the top, then since so let's see, let's step by step. So for each point on the top, with the coordinates x, y, z, then z is given by, because of this equation, z is given by 2 minus x minus 2y. Okay, therefore the height function is two minus x minus 2y minus the bottom. This is the top. And in our problem, the bottom is easy, just a 0, because on the bottom you have the xy plane, so 0 here. So 2 minus x minus 2y, this is your height function. Okay, therefore the volume is given by the integral of 2 minus x minus 2y over triangle OAB. Now this is a standard double integral as what we did in previous examples. So that's a key idea in all mathematics. You reduce the new problem to an old one. Okay, next we just follow the standard procedure, figure out what is OAB. So for this purpose, I will draw XY plane in 2D. This is O and this is A. This is B. Okay, so it is clear, we can view triangle OAB as a type 1 domain. And here, A is the origin, therefore A is 0. Next, we will figure out B. So what is B? So notice that B is the intersection point of 3 planes. Sorry, noted that. Oh, so my bad notation. Here B, never mind. So here A corresponding to small b, capital B corresponding to small a. So I'd better change the order of capital A and capital B, but I think you understand that. So noted that A is the intersection of 3 planes. So first, of course, you should have z equals 0, that is the xy plane, and then you have x equals 2y when restricted down to xy plane, that is OA. So OA corresponding to this, and the xy plane corresponding to this. And lastly, you should have AB. So what is AB? AB is a restriction of x plus 2y plus z equals 2. Okay, then let's solve it. So if you plug 1 into 3, then you have x equals 2y. X plus 2y is 2, and z equals 0. And then you plug 4 into 5. Then you have 4y equals 2, z equals 0. And therefore, y is 1/2, x is 1, z is 0. So the point is 1, 1/2, 0. Therefore, B is 1. Okay, next, as before, we need to figure out the top. So the top is this guy. The bottom, sorry, the top is this guy. The bottom is this guy. So notice that we should write down the top line as a function of x. So write blue line as a function of x. So how do you do that? Notice that since AB is the intersection of z equals 0 and x plus 2y plus z is equals 2, then you just plug it in. We don't need z coordinates here anymore, therefore we just drop it. So you have this, and hence y is 2 minus x over 2, 1 minus x over 2. And then similarly, the red line is given by y equals x over 2. Now we can calculate the double integral. So recall the volume equals 2 minus x minus 2y dA, and then if you write down as iterated integral, the x variable is from 0 to 1. The y variable, because the blue line is on the top, so you have 1 minus x over 2 here and x over 2 here, and inside you have this function. Okay, then let's calculate it. So you have 2y minus xy minus y squared, 1 minus x over 2, x over 2. And then you plug in, you have 2 times 1 minus x over 2 minus x times 1 minus x over 2 minus 1 minus x over 2 square, and the minus 2 times x over 2 minus x times x over 2 minus x over 2 square. Okay, now let's simplify. You have 2 minus x plus x squared over 2 minus 1 plus x minus x squared over 4 minus x squared over 2 minus x squared. Sorry, here I made some mistake. Here you should have plus, you should have small parentheses here. Therefore, after you do calculation, here you have plus, okay, and then plus x squared over 4. Okay, now we have cancellation. This cancel out with this, and then for the constant term, you have 1, and then for the linear term, you have linear terms. You have this. So minus 2x, and then for quadratic terms, you have this. Okay, so this is what you have. And finally, we do this simple integral x minus x squared plus x cubed over 3, 1, 0. So it's 1 minus 1 squared plus 1 cubed over 3, which is 1/3. Okay, so this is an example for the application of double integral to calculate the volume of some solid. Next, I will show you one tricky example. Well, although you can view it as type 1 or type 2, but to get the explicit integral, the only convenient way to do that is view as one type domain. So the problem is evaluate the integral of sine y squared. Y is between x and 1, x is between 0 and 1. So first, let's draw the picture for the domain. So here the domain is given by x is from 0 to 1, and y is from x to 1. Therefore, what do you have is this part. Okay, and then this is a geometric description, but if you look at the integral, then the problem is we don't know the antiderivative of sine y squared explicitly. You can try many methods, but the fact is you cannot simplify it to some reasonable function. Okay, then how to calculate this? Later on, if you learn some complex analysis, then probably you may have other ways to do definite integral by computing the residue. But here we introduce some tricky method. View this as a double integral. And by Fubini theorem, we can calculate in a different order. So what does that mean? So if you look at this iterated integral carefully, then you will find here we are viewing the blue triangle as a type 1 domain. What if we view it as a type 2 domain? Now let's change everything to type 2 domain setting. So here y, then y is between 0 and 1. So recall this line is y equals x. Therefore, x should be within 0 and y. Okay, Then the integral, let me denote as I. So I can be written down as the following iterated integral. Y is from 0 to 1, and x is from 0 to y sine y squared dx. And then the inside function is a constant, which is with respect to x. Therefore, finally, you have this integral to evaluate. Now the tricky part is you can use chain rule here. So the antiderivative is cosine y squared negative 1/2. If you take a derivative of this function, you will get this one with respect to y. Okay, then evaluate at 1 and 0, and you plug in. When you plug in 1, you have negative 1/2 cosine 1. When you plug in 0, you have 1/2. So you have this one. Yeah, I just want to give you some different flavor, how tricky the interchangeable integration order will be. Actually, this plays a great role in even in my research. When I want to evaluate something which is impossible from one point of view, you change the order, and then you can do some detour. So here I should say interchange the order of operations is very important. It's a very important technique in mathematics. And even in combinatorics, there are some similar ways. So in that category, we usually phrase it in the following way: count in two ways. And then, of course, you will have some equality. Okay, I will stop here for this lecture. Next, we will continue the curved domain by polar coordinate method.